Hello everyone, welcome to my channel. Today we are covering the most important topic of this chapter concerning to your university exam. That is the designing of tension member. It comprises with two cases, that is type 1 and type 2. Designing of rectangular plate as tension member, and type 2 is your designing of angle section as tension member. So in this video we will cover the type 1 part and we will try to solve a numerical based on this topic. So let's start. So type 1 is designing procedure of simple rectangular plate as tension member. So step 1 is your given data in which you have to mention all the data which are given in your numerical or question. Step 2 is to find factor load. If your question contains service load or working load, then you have to calculate the factor load by multiplying by 1.5. Nowadays the question comprises with factor load directly. So if factor load is given in the question, you don't have to multiply with 1.5. You can directly write the given value. Step number 3. Required net area on the basis of rupture. You have to find ANR, which will be equals to factor load into gamma m1 upon 0.9 into FUP. Now, to know the expected gross area, you have to increase ANR by 25%. Therefore, AGE will be equals to 1.25 into ANR. Step number 4. Required gross area on the basis of yielding. Now you have to find AG, that will be equals to factor load into gamma m0 upon Fy. AGR will be maximum of AG or expected gross area. So you have to choose that value which will be maximum of these values. Now step number 5, that is dimension anticipation. In this step you have to assume thickness of plate as per your wish. You can assume 10 mm, 12 mm or 16 mm. Then you have to calculate the width of the plate by dividing the gross area with assumed thickness of the plate. Now consider bolting in one line and then calculate net area of the plate, that is ANP, which will be equals to width minus number of bolt into dia of holes into thickness of plate. This ANP should be always greater than ANR, that is required net area. Now step number 6, design of connection. So first find net area of the bolt, that is A and B, that will be equal to 0.78 into pi by 4 into d square. Second is your shear strength of the bolt, that is VDSB. As I have taught you earlier, it is number of shear plane into A and B into FUB upon root 3 into gamma MB. Now you have to find minimum pitch and edge distance to find out value of KB. After knowing the value of KB, you can directly put this value in finding bearing strength of the bolt. Then find the number of bolts by dividing factor load by bolt value. After completing this step, you have to draw the diagram. Step number 7. Check for design parameters. As we know that tension member has 3 main design parameters, that is your strength in yielding, strength in rupture and strength in block shear failure. So on the basis of yielding, you have to check that a TDG will be equals to gross area into Fy upon gamma m0 and it should be always greater than factor load. If this situation satisfies, then it is hence okay. Similarly, on the basis of rupture, you have to find TDN, that is 0.9 into AN FUP upon gamma m1 and it should be also greater than factor load. If this situation satisfies, then it is okay. Third, on the basis of block shear failure, you have to first find AVG, AVN, ATN and ATG. Then you have to find TDB1 and TDB2 and the minimum value will give you the value of block shear failure. And this block shear failure should be greater than factor load. And if this situation satisfies, then it is okay. Step number 8 is to find the slenderness ratio. The slenderness ratio is equals to effective length of the tension member upon minimum radius of gyration, and it should be smaller than 400. And if this situation satisfies, it is okay. Step number 8 is optional if effective length is not given in the question. So friend, this is the design procedure of the tension member. Let's start with its numerical. So the question says that a tension member 0.95 meter long is to resist a service dead load of 20 kN and service live load of 60 kN. Design a rectangular bar of standard steel, that is Fe410, and use grade of bolt 4.6 where diameter of the bolt is 16 mm. So let's start. So we will start from step number 1, that is given data. So in given data we can mention various data that is given in question, that is grade of steel, that is Fe410. Therefore Fy will be equals to 250 MPa and FUP will be equals to 410 MPa. Grade of bolt is 4.6. Therefore FUB will be 400 MPa. Dia of bolt is your 16 mm. Therefore dia of hole will be equals to 16 plus clearance, that is 2, will be equals to 18 mm. In the question it is given that service dead load and service live load. Therefore total service load will be equals to 60 plus 20, that is 80 kilo Newton. Now let's go to step number 2. We have to find factored load. As these loads are not factored, therefore factored load will be 1.5 into total service load, that is 60 plus 20. On solving this, it is coming 120 kilonewton. Now step number 3, that is required net area. A and R will be equals to factor load, that is 120, into gamma m1, that is 1.25, upon 0.9 into FUP, that is ultimate strength of the plate, that is 410. On solving this, it gives 406.5 mm square. You have to convert 120 into Newton. Therefore, we will multiply 10 to the power 3. On solving this, we will get 406.5 mm square. Now we have to find expected gross area. Therefore, AGE will be equals to 1.25 of A and R. So, putting this value in A and R, that is 406.5 mm square will be equals to 508.13 mm square. Thus we have an idea that gross area should be near or greater than this value. Now step number 4, required gross area on the basis of yielding. So Ag will be equals to factor load into gamma m0 upon Fy, that is 120 into 10 to the power 3 into 1.10 upon 250. On solving this we get 528.3 mm square. Therefore, required gross area AGR will be maximum value of AGE or AG. So in these two values, this value is greater one. Therefore, taking AGR as 528.3 mm square. Step number 5, that is your dimension anticipation. So first assume the thickness. So I am assuming thickness to be 10 mm. Now calculating the width of plate. That is B will be equals to AGR upon T assumed. Therefore AGR will be 528.3 upon TA, that is 10. So we get 52.83 mm. So since it is very hard to fabricate a plate in this dimension, I am assuming this dimension to be 60 mm. Therefore, revised section of plate becomes 60 into 10 mm square. Now I will consider the bolting in one line. So considering boltings in one line. So net provided area when bolting in one line should be equals to ANP equals to B minus N, here N will be 1 as bolting is in one line, into diaphragm, that is 18 into thickness of plate. Here B is your 60. Therefore, on solving this equation, we get 420 mm square. Now step number 6, that is your design of connection. So first we will find A and B, that is net area of the bolt, that is 0.78 into pi by 4 into d square. On solving this we get 157 mm square. Now we will find shear strength of the bolt, that is VDSB. VDSB will be equals to number of shear plane into A and B into FUB, that is ultimate strength of the bolt, upon root 3 into gamma MB. Therefore N is here, that is number of shear plane is 1. If question says that the tension member is back to back connected such that gusset plate is sandwiched between them, then the number of shear plane will become 2. So in this case there is no such consideration, therefore we will take N is equals to 1. On solving this we get 29.00 kilonewton. This value gives in Newton, I have converted in kilonewton. Now we have to assume minimum pitch edge distance and we have to find value of kb. Therefore P minimum is equals to 2.5 times of diameter of bolt. So it is coming 40 mm. So I am assuming this value to be 45 mm. You can assume as per your wish, but it should not vary much. Now end distance or edge distance, that is 1.7 into dia of hole, so it is coming 30.6 mm. So I am considering this to be 35 mm. Therefore now finding the value of kb. Kb will be equals to minimum value of E upon 3dh or pitch upon 3dh minus 0.25 or FUB upon FUP, or it should be equals to 1. So kb value should be minimum of these 4 values, that is this value, this value, this value and this value. So kb value will be minimum of this value, therefore kb value will be equals to 0.58. Now we will find bearing strength VDPB, which will be equals to 2.5 into kb into d into t into FUP, that is ultimate strength of the plate, upon gamma MB. So putting these values we get 76.09 kilonewton. Therefore bolt value will be minimum of these value, that is 29 kilonewton and 76.09 kilonewton. So lesser value is 29, therefore bolt value will be 29.00 kilonewton. Now we have to find number of bolts, that is factor load upon bolt value. So factor load is 120 kilonewton and bolt value is 29 kilonewton. So it is coming 4.137. Therefore, number of bolt will be equals to 5 bolts. Thus, now we can draw the diagram. So suppose consider a gadget plate in which our tension plate is connected. So our diagram will look like somehow like this, in which 45 is your pitch, 35 is your edge distance, and width of the plate is 60 mm. Therefore, step number 7, that is check for design parameters. So first parameter is your on the basis of yielding. That is TDG will be equals to 600, that is gross area, into Fy, that is 250, upon 1.10. On solving this, we get 136.3 kilonewton, which is greater than factor load. Hence, it is okay. Similarly, on the basis of rupture, TDN will be equals to 0.9 into net area of the plate, that is 420, into ultimate strength of the plate, that is 410, upon 1.25. On solving this, we get 123.9 kilonewton, which is also greater than 120 kilonewton. Hence, it is okay. Now, to check on the basis of block shear failure, first we have to find AVG, AVN, ATG and ATN. So I have taught you in earlier classes that how to find AVG, AVN, ATG and ATN. So first we will find AVG. The AVG will be equals to 215 into 10, as in gross area we do not consider any bolt hold. Therefore, it will be equals to 2150 mm square. Now, AVN will be equals to 215 minus number of bolt hole. So you can see that there are 1, 2, 3, 4 and this one is half, that is 4.5 into 18 into 10. So on solving this, we get 1340 mm square. Now we have to find ATG. Now ATG will be equals to this part, this is your tension part, that is 30 into 10, that will be equals to 300 mm square. Now we have to find net area of the tension plane. So net area of the tension plane will be only this part. Therefore, it will be equals to 30 minus half dia, that will be 0.5 into 18 into thickness of plate, which will give 210 mm square. Therefore, putting these values in TDB1, we get 344.1 kilonewton. Similarly, we will put these values in TDB2, we get 296.5 kilonewton. Therefore, strength in block shear will be TDB is equals to minimum of this value, that is 296.5 kilonewton, which is greater than factor load, hence it is okay. Now step number 8, we have to find slenderness ratio, that is lambda, that will be equals to effective length upon R minimum. Therefore, here R minimum is minimum radius of gyration, that will be equals to second moment of area upon gross area. On solving, we get 2.88 mm. Therefore, putting this value, we get 329.86, which is smaller than 400. Hence, it is okay. Thus, we have completed the part 1 of the designing. So friends, if you like this video, please like, subscribe and share. Thank you.